Fantastic. So let's do our Python version of this 1D bar problem that we did yesterday, and see what's involved. And I want to show you it's really not that long. It's quite short. Okay, so that is really what is there. So let's go and see for ourselves what we can do. Okay. So first off, I'm just going to use NumPy and keep it numerical. Okay, so this is not going to be SymPy. We are now moving into a fairly numerical version of part of the course. So from now on, most of the stuff that we'll do when it comes to final elements, or everything that we'll do essentially will be numerical. Okay, numerical combined with numerical integration. So this is why we're not busy with SymPy at this stage. Just take note of that. First off, we have to mesh our geometry. So we have a bar, and we're putting our coordinates in space. And so we're putting down nodes in space. So we're putting down 3 nodes, and at each node there'll be an associated unknown. So that is just the nature of it. So every time we put a node down, there's an associated unknown displacement associated with that in 1D. In 2D, it's obviously 2 displacements, displacement x and y, and 3D would be 3 displacements. Okay, but this is our meshing that we're doing. So we put on x1, x2, and x3, the same way as we did in class. I define the material. Take note, everything that I define is a function of z. It might not vary as a function of z, but everything is a function of z. So the material, the area, so just take note of that. Okay. So then what I have is essentially shape functions n1, 2, 3, just coding them in, taking tie as input, returning the shape function values. The derivatives I can set up. So that's the derivative of the n1 with tie, the n2 with tie, the n3 with tie. That's just that, coded in. Then I have the sort of first step towards constructing the B matrix, which is the first part is the ND tie. That's that first term, or the vector term, and then we still require this to complete the B vector, or the B matrix. Okay. And we're all going to call it B matrix, just so it generalizes easier to do later on. Although it's a vector in this case, in general, it's not. So that's that. Then I use the isoparametric formulation. So isoparametric means we can relate the x values, the x coordinates that we have on our mesh, relate them via the shape functions to x. That's what we have, and these shape functions are a function of tie. Okay. Then we can take the derivative of this, which is again just the n d tie times the nodal values. Okay, so that's what's compute here. Okay, that is then dx d tie. Set up the V matrix. One of it, the x d tie times the n. That's what we have there. Then define the area, which is given as 0.02 minus 0.001 x. And here I just put in x as a function of psi. Now a is a function of psi as well. The reason why this is again important, when we have our integrand, everything has to be a function of psi, because we're going to use Gauss quadrature to integrate. So now I've got x, okay, completely as a function of psi, and here's my integrand. This is what I need to integrate, okay, from -1 to 1. And here are my, so we can just quickly go through this. Young's modulus, outer product of B with respect to B, although that is the same as B transpose times B. Remember, B is a 1 by 3 matrix. The B transpose is a 3 by 1, and then times B is again 1 by 3. Will give you a 3 by 3 matrix. This is why we use the outer product of NumPy. Okay, the outer product between two vectors, AZ and dx dz. Okay, so that's that. Then we have the Gauss quadrature points and the Gaussian weights. It allows us to do the integrand that we can integrate now, and just look at the inconvenience. Remember what you did by hand previously? It was those 6 components that you had to integrate because of the symmetric parts. Okay, those diagonals, all of them individually. Just look at the convenience now of just evaluating k at a specific coordinate, this k at another coordinate in the psi space, multiplied with the right weight, adding the two together, they have integrated the whole matrix. Beautiful, beautiful. And this is part of what makes the finite element method so elegant to compute on computers. So everything that the choices that were exercised here were two things, two reasons behind those choices. The one was to make sure we keep what we're doing mathematically very easily interpretable, so we can verify and check. And the other thing is to make sure it's very, very efficiently computable. And those were the two things. And you could see here how that's the case. Okay. And then we apply the load. And again, the load, this is associated, each one is associated with a node. And what we see is here, we apply load at the second node. Okay. And the second node is essentially at x equals to 1. So you can also go and double check that it's nothing funky or funny there. This is it. That's now set up the system. So this setups the K matrix, and this setups the applied loads. All that you have to do is now to say, well, not all of these Q's are unknown. The first one is known, is a prescribed displacement. So that's already known to be 0. So we only have to solve for Q2 and Q3. So we partition our system and our force vector, and we can take that column that multiplies with the 0 also towards this side. But in essence, then we end up with a system that we can say, let's solve it. Okay. Then we can solve for those Q2 and Q3. And all I'm doing is I'm using NP-ln-alg solve matrix, and the right hand side, or the applied loads on the right hand side. There's my solution. Now, once I've got the solution, remember from the beginning of the course what I told you? If we know the displacement field, we know the material and the geometry, we know everything about the problem. And here we have now, essentially, we are able to construct the displacement field as a function of psi over the local coordinate, over the psi local coordinate. This is what we're able to do. Isn't that beautiful? So the reality here is that we're now in a position to say, because we have the displacement field, we've solved everything. Now the rest is post-processing, and this is how it also works in the finite element method. Is you work to get to the point where you've got the displacement field. We set up now the complete displacement field. Please note I include here Q1, which is the known displacement, as well as the two ones that we solved for. So this is the full displacement field. Now from that, one can do some post-processing and say, okay, great. So that allows us to compute, now that the whole Q and all the unknown nodal displacements are known, we can compute the strain. Remember what the strain was? The strain was just PQ. So here is, if I want to give many Z's, I can now go and compute the strain field for those many Z's. So let's check what happens. Here's essentially, I'm building up just a result list. Here's my nodal displacements. And here's just a zeta in a Z. So this is one value in that, maybe a potential vector of Z's. And then all I do is say, just append to this list the result, which is just BQ. And what we append is just BQ. Yeah, remember that? BQ is what we had for strain. So that's just a dot product between B and Q. That will give us a strain out. Okay, and then I return the result. So now what we do is we just plot over the local coordinate, we plot U strain, strain times Young's modulus, which is the stress, strain times Young's modulus times area, which is the internal force. Make sure my unit is right here, internal force. Alright, and if I run that, I've got the solution. And now what I want you to do is, I want you to open up the other notebook. Okay, so let's just look at this quickly. So we can also just print stuff a little bit. So let me just open up here at the bottom and say, what is Q? What is the displacement that we got? 0. The displacement at the end node was 3.2967. Okay, if you go back to our solution that we had, this is now going to solving the problem with the weak form. This is the one that we did the first time. Okay, so that was that one where we assumed this quadratic displacement field in the x coordinates. I want to remind you what the values were here. So let me see if I can quickly get to those values again of the displacement field. Where was it? U. Okay, and I think here I evaluated U. Let me just check here quickly. What is U if I just plot it? Okay, so let's evaluate U at 1. Ugh, is it now symbolic? what I want you to see is look at that, the end value of the end node, 3.29670. So let me just cut this out, times 10 to the minus 5, okay? Just want to be comparing that. Just look at that comparison. 3.2967033. And so what you see is numerically these two solutions are equivalent. Let's double check. What about the mid-side node? Middle. How many typos in one? Can you make it 30 seconds? Okay. So if I look at that, 1.3736, where was it? 63736 up and up. Can you see that? Numerically, these solutions are equivalent. And it would be my expectation as well, because here we assumed a quadratic solution. The only difference was the A, B, and C here didn't have nice meaning. So the A wasn't like the displacement at a specific point or anything. It had an influence everywhere. So if I wanted to know what the displacement was at this point, I have to substitute x at this point, have this term contribute, that term that contributes, and that term that potentially contributes towards the displacement here. And the same for here and the same for here. So we can't interpret these A, B's, and C's very elegantly. It's easy to make a mistake. Okay. Now if you look at the solution here, I know exactly what this is. This is the displacement at the left edge. This is the displacement at the right edge, because that's my second coordinate, which is the right side. And this is the displacement in the middle. Isn't that elegant? Now we can really go and easily verify things. Okay. So the solutions are equivalent. So my expectation is that you need to go and verify for yourself. Go and compare the strains, go and compare the stresses, and go and compare the internal forces. I just want to put the internal forces up that you can just visualize it and just put it back. Look at that range of values there, between 920 and 1040. And you can just quickly verify for yourself and say between 920 and 1040. Beautiful, isn't that? So now you can see we've computed exactly the same solution as before. The only difference is this time we used a single finite element. Okay, so this concludes this example. Let's head off to the next example.